at presenting our groundbreaking zero divided by zero systems concept, symbolizing infinite potential and zero waste. I'm an independent researcher based in Santo André, Brazil. Our project, the Arc of Humanity, is dedicated to preserving life beyond limits by developing a comprehensive lunar waste recycling system that not only sustains extraterrestrial habitats but also revolutionizes waste management here on Earth. Please take a moment to view our detailed portfolio on Google Drive, which showcases our past work, vision and innovation. Our proposal integrates advanced recycling technologies, digital twin simulations, and ecological principles to build a self-sustaining lunar habitat. At the core of our approach is the revolutionary zero divided by zero systems concept, which embodies both zero waste and infinite potential. We leverage AI-driven process optimization to monitor real-time sensor data and dynamically adjust operations. In our system, every fraction of waste is captured and transformed into valuable resources, and even residual byproducts are reprocessed into energy. Additionally, we combine modular additive and subtractive manufacturing, enabling us to rapidly produce and adapt components as needed. Strategically, any prize funds we receive will be directed to the University of Alabama. This collaboration will provide access to world-class research facilities, foster joint Brazilian U.S. projects, and ensure transparent use of funds to refine our prototype, perform extended testing under simulated lunar conditions, and accelerate the innovation process. 2 to 315, Recycling and Manufacturing Process Overview. Let's explore our recycling process. Our system targets key waste streams expected in an 8-person lunar habitat. Plastics, encompassing packaging materials, plastic containers, and rigid plastics, about 40% by mass and 35% by volume. Textiles, fabrics covering clothing, towels, and fabric scraps, roughly 30% by mass and 25% by volume, unified into a stream of about 1,000 kilograms and 10 cubic meters. Metals, including structural scraps and maintenance residues, about 20% by mass and 25% by volume. Composites, such as carbon fiber reinforced plastics, roughly 10% by mass and 15% by volume. We also address supplementary streams like foam packaging, EVA waste, and food packaging. For plastics, we use controlled pyrolysis to produce recycled polymer pellets, yielding around 450 kilograms per day from 500 kilograms of input. Textiles are processed via hydrothermal methods to recover fibers, about 120 kilograms per day from 150 kilograms of input. Metals are refined into high-quality ingots, approximately 180 kilograms per day, and composites are separated into fibers and resin fractions for further use. These processes are all designed to work together in a closed-loop system, ensuring that every fraction of waste is transformed into usable feedstocks or energy, integrated recycling modules. Now, let's examine the individual modules that make up our system. First, the pre-sorting and identification unit uses XRF and Raman spectrometers along with high-resolution vision systems to accurately classify incoming waste. This ensures that every item is properly routed. Next, our fragmentation and shredding module reduces waste into uniform fragments using high-torque shredders with carbide-tipped blades, followed by vibratory screens that sort particles by size. Then, the separation and purification module employs magnetic, centrifugal, and filtration systems to isolate different materials, ensuring pure streams of plastics, textiles, metals, and composites. Following that, our conversion and manufacturing module transforms these sorted streams into recycled pellets, ingots, and other feedstocks through extrusion, pyrolysis, and electrorefining. Finally, the energy recovery module captures residual heat and chemical energy, converting it into electrical power to sustain continuous operation. All of these modules are integrated and controlled by our digital twin and control system, which uses real-time data and AI to adapt processing parameters, ensuring maximum efficiency. On screen, you'll see detailed CAD renderings and animations that demonstrate how these modules interact in a fully integrated, closed-loop process. For 30 to 530, concept of operations, production cycle. Let me walk you through our full production cycle. Waste intake and pre-sorting. 10 minutes segment robotic arms deliver waste into our pre-sorting unit, where sensors quickly classify it by type and contamination level. Fragmentation and shredding. 15 minutes segment the waste is shredded into uniform fragments by high-torque machines, then sorted by particle size using vibratory screens. Separation and purification. 15 minutes segment advanced separators isolate the individual materials, ensuring that plastics, textiles, metals, and composites are purified and ready for conversion. Conversion and manufacturing. 20 minutes segment each material stream undergoes a dedicated conversion process. Plastics are repolymerized into pellets, textiles are processed to recover fibers, metals are refined into ingots, and composites are separated into constituent components. Finishing and output collection, 10 minutes segment. Finally, the processed outputs are collected, sorted, and either stored or directed into further manufacturing processes. The entire cycle lasts about 1 hour, allowing for 8 to 10 cycles per day. Our system is designed for minimal crew involvement. Most operations are monitored remotely via our digital twin dashboard, with only essential maintenance performed by 1 to 2 crew members per shift. 5:30 to 6:30, Hardware and Components Overview. Now, let's take a closer look at the physical components that make up our system. Our detailed CAD models illustrate the layout and key dimensions of every module. For example, our pre-sorting unit, which occupies approximately 1.2 million cubic centimeters, is designed with precise access panels and mounting interfaces for maintenance. Our equipment list details every module. The fragmentation and shredding module weighs around 200 kilograms, the separation and purification module is about 300 kilograms, the conversion and manufacturing module comes in at 350 kilograms, the energy recovery module weighs 250 kilograms, and our digital twin and control system is a compact 100 kilograms unit. Additionally, our auxiliary systems, comprising conveyors, safety enclosures, sensor mounts, and access panels, ensure smooth material handling and quick maintenance. All components operate within the required environmental conditions, 0 to 50 degrees Celsius, 90 to 110 kilopascals, and are designed to work seamlessly together, embodying our commitment to zero waste. 6:30 to 7:30, Development Planning and Risk Management. Moving forward, our development plan for Phase 2 is structured into 3 key phases. Phase 1, months 1 to 6 focus on material testing and subsystem validation. We will finalize detailed CAD models, run simulation analyses, and prototype key subsystems under simulated lunar conditions. Phase 2, months 7 to 12 develop a fully integrated prototype. We will fabricate custom components, integrate all modules, and conduct rigorous tests in a controlled laboratory environment that simulates lunar conditions. Phase 3, months 13 to 24 full system testing in preparation for potential lunar deployment. This phase involves assembling a field-ready prototype, running extended tests in thermal vacuum chambers, and refining the design based on performance data. We have also performed a thorough risk assessment. For instance, we will mitigate thermal failure by using advanced heat-resistant materials and optimized cooling, and address integration challenges through standardized modular interfaces and incremental testing. Our preliminary Phase 2 budget is estimated at $1,600,000, funded through our Phase 1 prize purse, partner contributions, academic partnerships, and external grants. On screen, you'll see a Gantt chart with milestones and a budget breakdown that clearly illustrates our timeline and funding plan, future impact and scalability. Our solution offers transformative long-term impact. It not only addresses lunar waste management but also provides adaptable, sustainable recycling technologies for terrestrial applications. With its modular and scalable design, our system can be expanded to support larger lunar settlements or adapted to revolutionize waste management on Earth, creating resilient circular economies that reduce resource dependency and environmental impact. We are actively pursuing partnerships with academic institutions, industry leaders, and government agencies. Our collaboration with the University of Alabama will provide world-class research facilities to further refine and test our prototype, opening extended research opportunities and fostering innovative projects across borders. This project sets the stage for a new era of sustainable space exploration and terrestrial resource management, where every ounce of waste is transformed into energy, raw materials, or finished products, ensuring a cleaner, more resilient future for all. 9 to 10 o'clock, Conclusion and Call to Action. In conclusion, our 0/0 Systems project redefines recycling and habitat design. By integrating advanced recycling technologies, digital twin simulations, and a modular design, we achieve near 100% material recovery and energy efficiency. This system not only meets the challenges of a lunar environment but also offers scalable solutions for Earth's waste management needs. We invite you to join us on this transformative journey toward a sustainable future, both in space and on Earth. Together, we can push the boundaries of innovation, ensuring that no resource is wasted and that life continues to thrive beyond conventional limits. Thank you for your time and support. Let's create